Okay, now I hope you'll work with me on this set of buffer problems. These are contained in the packet that you purchased from the bookstore. We'll go over blood buffering in a separate, shorter video, but we're going to start with those buffer problems. The first being a problem in which we have a solution or a buffer system made up of 30 molar formic acid and 0.52 conjugate base. So that's molarity also, COOH minus, okay? So we want to calculate the pH of this buffer system. So essentially you can create a buffer system for any pH that you need for whatever purpose you need it for. There are two ways that we can calculate the pH of a buffer, and I'm going to show you both. I want you to be able to calculate it both ways. Now in Gen Chem 2, you should have been introduced to acid dissociation constants, and that's the first method we're going to use. So that means we're going to need a case of A for formic acid, and that case of A, that over a little bit, sorry, is 1.8 times 10 to the minus 4. Okay. Now, if you recall, when you're working with weak acids and weak bases, they do not ionize 100%. So there's an equilibrium present. And that equilibrium, in this case, would be HCOOH, or the equation, double arrow, showing that it is not 100% ionized. And on the other side, we have hydrogen ion and the conjugate base of that weak acid. Okay. So remember, this is an organic acid, so this is the acidic hydrogen. That is the one that's going to ionize in this case. And we will have an equilibrium between the weak acid and its conjugate base. And of course, we'll have an equal amount of hydrogen ion here. So, recalling that the case of A equals the concentration of H plus whatever that conjugate base is, and in this case, it's HCOO minus, and that is all divided by the concentration of the weak acid. Okay. So we have our we have our case of A, so we just plug that into our equation. And that equals the concentration of the hydrogen ion, which we don't have, but we do have the concentration of the conjugate base and the weak acid, so we will just plug those values in to our equation and solve for the concentration of hydrogen ion. Then we can use negative log of the hydrogen ion to calculate our pH. So in this case, hydrogen ion concentration equals 1.0 times 10 to the minus 4. And pH equals negative log of that concentration. So our pH then is 4.00. I don't know if you remember the rules for sig figs when it comes to reporting pH, but it is one more decimal place than the number that you use to calculate that pH. In that case, we had one decimal place, and we need 2 in our pH. I'm not a stickler for you reporting pH to the correct sig figs necessarily, but you should know how to report them correctly. The other way to calculate pH is using what's called the Henderson-Hasselbalch equation. And that we've seen in one of the slides. Again, it's pH equals the pKa plus the log of whatever the conjugate base is. I'm going to use a generic representation here, over the concentration of the weak acid. And remember, the pKa can be calculated using or determined by taking the negative log of the K sub A. And in this case, the pKa then is going to be negative log of the K sub A, which is 1.8 times 10 to the negative 4. So our pKa equals, where is it? 3.74. Sorry about that. I lost my place there. Now we can just plug that into our Henderson-Hasselbalch equation. And we'll add to that the log of 0.52 divided by 0.30, and our pH using the Henderson-Hasselbalch equation is 3.97. So essentially 4.00. So again, I want you to be able to use both methods to calculate pH of a buffer system, because I'll ask you to do it both ways on an exam. So the next problem in your packet involves a couple different parts, actually 2 parts, I guess it is. And in this case, we're using a buffer composed of ammonia and which is a weak base, plus its conjugate acid. And we again are going to determine the pH of this buffer solution that is 0.30 molar in ammonia and 0.36 molar in a salt, ammonium chloride, that contains the conjugate acid of this weak base. Now in this case, we are given a K sub A. And the K sub A, again, would be for that ammonium ion, which is acidic. And that K sub A is 5.8 times 10 to the negative 10. K sub A's, of course, will be given to you on an exam. If you are working problems from your book, I recommend you use any K sub A's supplied in the text. If they're given, I don't recall if there's a table there. But if you're looking them up on the internet, you might find variation in K sub A's. So we're going to take that 2-part approach again. I'm going to work it first as an equilibrium problem, as you would have, again, in Gen Chem 2. And in doing so, then, our K sub A is going to equal the concentration of hydrogen ions, times the concentration of ammonia, divided by the concentration of the ammonium ion, which again is a weak acid. So ammonia is the conjugate base. So again, we'll determine, and sorry about that, I want to write the value of that K sub A. We'll determine hydrogen ion concentration. And we have 0.30 molar ammonia. We'll divide that all by 0.36 molar for the ammonium ion. And our hydrogen ion concentration then equals 6.96 times 10 to the negative 10. Calculate pH, taking the negative log of that concentration. And our pH of this buffer is 9.16. So the first buffer solution was in an acidic range. The second one is in a basic range. keep in mind that buffer solutions have the ability to buffer 1 to 2 pH points above and below that pK. And we'll look at that again on some titration curves of amino acids, actually. And so once again, we can do this as well using the Henderson-Hasselbalch equation, in which case we'll have to calculate the pKa, negative log of the K sub A. And I will also have you calculating the pKa's. So, pKa here equals 9.24. So the pH of this buffer solution is 9.24 plus the log of 0.30 divided by 0.36. pH equals 9.16. And these two match exactly. Sometimes, depending upon the pKa calculation, you might see a little variability in the final pH between these two, but in this case, we're right on the money. Okay, so the important aspect then of a buffer is to neutralize small amounts of acid or base that are added to that buffer solution. So in the second part of this problem, we're going to look at what happens to the pH of a buffer when we add a specified amount of sodium hydroxide. So we have ammonia in this buffer, and we have the ammonium ion in this buffer. And they are in equilibrium. So when I add hydroxide ion to this solution, it will be neutralized by the weak acid. And we will get more ammonia and water as a product there. Okay. So in order to calculate the pH of this buffer system after I add that hydroxide ion, I need to determine how many moles of that weak acid I'm going to neutralize or will be utilized neutralizing the hydroxide ion, and how many moles of ammonia are going to be produced. So if you remember those things we called ice tables, we're going to utilize that. So we're going to have initial concentration, change, equilibrium concentration. And I believe this was 1 liter of solution, or maybe it wasn't, but bottom line is whatever amount we have, actually I think we have, well, let me see here. Oh no, in this one we're using 80 mils. Okay, so we have to find out how many moles of ammonia, ammonium ion, and hydroxide we're using here. Okay, so first calculation, I'm going to calculate the number of moles of hydroxide ion. This was sodium hydroxide, strong base, 100% ionization. And we're adding, looks like 20 mils. So converting that to liters, we have the molarity of 0.050 mole per 1 liter. So the number of moles of hydroxide ion that are added to the buffer are 0.0010 moles. Okay, so that's going to be our change. Number moles of, I've got ammonium first. This we have 0.0800 liters that we're starting with. Whoops, I should have put that down a little further. And this is 0.36 moles in 1 liter. So we have 0.0288 moles of ammonium ion. And then finally we'll calculate the number of moles of ammonia that are present. Again, we've got 80 mils of this buffer. Convert that to liters. And this concentration is 0.30 mole per liter. So we have 0.0240 moles of ammonia. Okay. So these are our initial number of moles before we've added that hydroxide ion. So we have 0.0240 here. We have 0.0288, and this is moles of ammonia. So we already determined that ammonium ion will neutralize that hydroxide. So that means that we're going to use up 0.0010 moles of that weak acid in the neutralization, and we're going to gain 0.0010 moles of ammonia. So doing that math, we end up with 0.025 moles of ammonia and 0.0278 moles of ammonium ion. Now, we don't have the molarity, and we need that molarity in order to do our calculation using the Henderson-Hasselbalch equation, which I believe I utilized, or maybe I did. No, I just used Henderson-Hasselbalch here. You could use the other as well. But we added 20 mils of sodium hydroxide to 80 mils of our buffer solution. So now our volume is 0.100 liters. So we have to divide both of those by the new volume to get the correct molarity of our solution. And then we'll plug that into our Henderson-Hasselbalch equation. And the new concentration of ammonia is 0.25 molar, and that's over 0.278 molar. And the pH of the resultant solution is 9.19. So the original pH of this buffer was 9.16. So we have just had an increase in that pH of 0.03 pH points. So we maintained, or essentially maintained, the pH of that solution or that buffer system. Okay, let's look at the next problem, number 2. I need to move that just to tab. There we go. We're given the case of A of acetic acid, or I'm giving it to you. The problem involves acetic acid, and that is 1.8 times 10 to the negative 5th. And we're asked to calculate the pH of a solution that has 0.400 moles of acetic acid and 0.500 moles of sodium acetate. So again, we're seeing a salt with the conjugate base of this weak acid, or we're seeing that. This is in 1 liter of solution, so we have our molarities. Our buffer is 0.400 molar acetic acid, and it is 0.500 molar acetate, conjugate base. And once again, we can use either method to calculate pH. And if you're getting these, fine. If you need practice, I've posted practice problems. I'm not going to set up the equation each time. We should be catching that, or we should have caught on to that by now. We'll calculate concentration of hydrogen ion using that equilibrium equation. And so hydrogen ion concentration is 1.44 times 10 to the negative 5, and pH, negative log of that concentration, and our pH of this buffer is 4.84. So again, we've got a buffer that has more acidic, in the acidic range. So I can also, again, use the Henderson-Hasselbalch equation to determine pH. Again, we need the pKa, and pH equals a pKa of 4.74 plus the log of 0.500 divided by 0.400, and pH equals 4.84. Okay. What happens after we add a small amount of hydrochloric acid to this buffer system? pH will vary a little bit, but will it go up or will it go down? Things to think about. Which way will that equation shift if you think in terms of Le Chatelier's principle? If we're adding HCl, what's going to neutralize it? Acetate. So that means we're going to create more acid. And I would expect to see that pH go down just a little bit. So in this case, we are going to add 0.0600 moles of HCl. Okay. This is still 1 liter of buffer solution. So we can set up an ice table. And oh heck, I didn't leave a whole lot of space here, but we have our weak acid, we have the conjugate base, and we know how many moles of hydrogen ion that is being added. So our original concentration of weak acid is 0.400 molar, and we have 0.500 molar, or moles, either way, of conjugate base. Again, the conjugate base is going to neutralize that hydrogen ion, so from that initial concentration, we're going to subtract 0.0600, and we'll make 0.0600 moles of weak acid. Equilibrium concentrations here, 0.460 and 0.440, to which we will just plug into the Henderson-Hasselbalch equation again. Uh, 0.440 over 0.400, and our pH is 4.72. So you can see that it did drop a little bit.